So, welcome to the next mini conference on Cortex-M, this time specifically on security. First, a short introduction. My background is IT in general, but more specifically, I've done the development and design of products all the way from NATO top secret data protection down to being the lead maintainer for what used to be called Polar SSL. Mbed TLS is the current name as part of Mbed after an acquisition by ARM. So in that scope, I'm currently leading our effort on defining the security specifications, but also the things we want to do with security on the device side of IoT devices. So not things in the cloud, but what do you do to protect the devices? And in light of that, I'd like to look at more generic differences between what are the differences between the Cortex-A security world that are well understood nowadays with mobile and everything we do with trust zone and a protected and unprotected side, and how that translates to a Cortex-M world, specifically also from the perspective of people that have experience in the Cortex-A side, but not necessarily the Cortex-M world, because they're different beasts to tackle. So to dive into that first, to put a bit of framing for people that don't have a deep background in Cortex-M, the Cortex-A Linux-like environments and Cortex-M environments have some major differences, and the most important one is the lightweight approach that you need to take on Cortex-M. For a few reasons. For one, the standard big operating systems that provide a lot of functionality across all layers and have all modules for providing security and functionality to the rest of the system are not there because there's no Linux running there. But also you don't have virtualization built into the chipset, so you don't have hardware support for virtualization, so you can't use that to separate items. And you're very resource constrained. Typical systems have a flash of 256K, maybe a meg, but that's really big. RAM size is all the way down to 64K, maybe to 512 if you're really, really lucky. And within that space, we need to be able to provide applications, but also do that security protection to make sure that we provide something similar to what we can do in Cortex-A to protect secrets, identities, and everything, but without the same capabilities of measures. In addition, there's a lot of actions, especially in security, that take a long time to perform, like public key operations, but there's real-time constraints on drivers like bit banging, specific ports that have to be adhered as well, and you don't have the same scheduling capabilities there. So in MCU environments, we have to directly use the hardware to do all the low-level actions, and we have to do all the things like separation, privileges in a single core instead of having separate layers and modules that work together as in the grand scheme of Linux and similar operating systems. So on an OS level, we need to provide some form of software partitioning to, for one, be able to boot that device all the way from power down to a secure state, again, in that single OS core that you have, and to have some form of ability to provide mutually distrusted boxes, as we call them within Mbed, but mutual distrustful boxes where you can make sure that if a part of the software or component wants to do something malicious on the device, it's not able to do that on other parts of the system. So the boxes are protected against each other. They have to protect from malicious code because of a hacker breaking into the Wi-Fi driver, for instance, because those are major parts of the system, millions of lines of code, very hard to definitively say that they are 100% secure. And because there's probably a single flash where it boots from, and every system normally has access to that flash. You have to prevent any of those components to be able to write to the flash, because that's where the firmware and thus the security of the booting actually lies and of the OS actually lies. So that's something that's different in MCU. And in addition, compounding that and making that harder is the fact that all the different Cortex-M MCUs have a lot of diversity. They have different programmers models, they have different CPU architectures, but we need to be able to span that all. And they differ a lot in the functionality that they can offer. Some have a timer that you can use, some have an external one, some have a TRNG, some have hardware acceleration, some don't. Some have an MPU, some don't. There's all kinds of different configurations, especially because the Cortex MCUs have a whole load of configuration options when silicon vendors try to differentiate between each other. So in order to cope with that, we need to make some form of portable security libraries that provide those separations, future bootstrapping, and everything. So one of those is Mbed Microvisor, which is our effort to provide a security microkernel that separates boxes. It does nothing else. It just makes sure that one box can't access the other. And it requires some form of common API to interact with all those boxes and to do the things there. And that's what, if you went to the talk yesterday of the platform security architecture, was talked about, to have some form of common APIs across the Cortex platforms to talk to those secure side. So that's the general framing of the situation as we see it. And what I did is I created a few questions where I would be very interested to hear your opinions about on how we can solve some of those issues. So if you look at the Cortex-A world, we use the trusted world to protect DRM mechanisms, enable features, and more like that. But in the Cortex-M world, these often don't apply. We don't really have DRM there because there's no video streaming going on. But what are the biggest threats that that are facing Cortex-M systems? So what do we have to protect against in Cortex-M systems and IoT systems? What do we have to take into account when we're building those secure side libraries and the physical securities in the future, maybe inside the CPUs? Dan, you need to stick.
Leakage of sensitive data would be an immediate one. So, health data or anything like that.
So that's definitely one that we need to take into account, especially if people are using more and more of medical smart devices.
So for me, it's secure boot and getting enough in these products that you can, for example, have fusible security certificates and getting enough commonality in people who make specifically ARM chips, but really any chips, so that you can have secure boot done in the chip itself.
Yeah, so secure boot is of course a mechanism that is already a measure against some form of threat. So what's the threat we're trying to protect against?
The threat there is uploading images that are bad to a device in some way. And those threats can either be over-the-air upgrades, which are obviously the most threatening, but even getting into the supply chain itself and replacing out, for example, flashes. One of the later concerns we had was when we had our production chain, when we had external flashes there, that somebody would come part of the way through that and actually put on a different flash after the device was manufactured, and then cause an issue there. So I think it's both in the manufacturing process, but then also once the device gets installed. Yeah.
And in this case, it's an external flash apparently. It's not one inside the MCU.
Yeah. In single chip designs, you have less of a risk there, but it would still be nice you still have to protect against over-the-air upgrades.
I would probably be the biggest thing I'd be worried about was side channel attacks, like a power analysis attack on the crypto, because this is going to use a lot of different crypto from a lot of different vendors, and to be confident that all of them have done the proper job of making sure that the power is constant and timing attacks are not viable. Really hard.
Yeah, that's definitely something to consider. I mean, that's of course the big issue now that we have with IoT. All the devices are more physically available to people. They're everywhere, so people can access them. There's of course mitigations, like making sure there's nothing in the device that you can that can break out to other devices. But that's definitely something to consider.
To me, getting access to the whole network, being a non-detected and being a non-detected sentient being in one device and having access to the rest of the network. So, I mean, one device being attacked, bad. Whole network being being compromised is catastrophe. So I think that's, to me, that's a big challenge.
Yeah. So the threat of group compromise, so that one class of device, one device can compromise the entire group of devices based on the same batch or whatever they're built on. Sure. Anybody else? Jeff?
Programmers, probably. But
What specific part of programmers?
I think
When they're sitting on their chair, they're fine.
I'm joking around. I guess one of the threats that seems most ignored might be denial of service. The proliferation of nodes. I mean, it wasn't long ago a car was a node. It's now one of the most complicated networks itself. And the consequence of being able to render any one of those ECUs, make it malfunction, shut it down, can trigger a sort of a domino effect because these nodes are so sort of organically stitched together into systems rather than systems per se being something that you have to defend. You're having to defend each of the individual components of it. So the ability just to break them rather than necessarily exploit them, because those are the kind of traditional problems we're so used to dealing with that I see they're less of a threat because we're aware of them. And these problems usually come when you're not looking. They don't occur where you are looking. And so I think that's not a kind of threat that we're used to dealing with in bigger nodes and in conventional computing.
Okay.
That's one.
For me, probably, and this goes back to what the gentleman there was saying, the compromise of a single device that can lead to compromise of multiple devices. But a specific use case where you have now with IoT a proliferation of heterogeneous devices, and some may be completely secure, but one isn't. And that chink in the armor is very difficult to protect against, and I think that's probably one of the biggest threats that I see as far as IoT is concerned.
Yeah, that's one that also hinges on your first comment, because it links well to Jeff's denial of service as well, because often similar devices are at similar points in the chains across the globe and the value chain. So if you find DOS in one of those devices, you can probably bring down the entire class, because that's not something you can protect against with unique keys or something. So those two compound each other even more. Okay, cool.
Just one more, maybe?
Maybe one back there. Can you get a microphone too?
Sorry, can you wait for the talking stick?
To riff on Jeff's point, actually I don't think it's so much developers so much as product managers and the time to market.
Is that product management or is that C-level management? But yeah, I agree there.
Just one more, cloning of devices.
Yeah, cloning identities and not being able to detect those. Yeah. So
One more, just real.
even one more.
One I haven't heard spoken about yet is verifying that the hardware is trusted hardware. So from a chip vendor perspective, I might be selling a chip and licensing the software that goes with it, but I want to make sure that somebody doesn't come around and bootleg some hardware and undermine my price points.
Yeah. Okay, those are, that's quite an extensive set of things we have to protect against that are risks for IoT devices. So a logical follow-on question is then, what are the services that we should provide on the secure side to protect against this? Because that's, of course, the next step. What do we have to provide in a chip, either on the hardware side or on the software side, to make sure that these threats can't happen in a systematic way?
You start with the basics, authentication and authorization for access to any portion of a device by, I guess the term is box and embed. So. Yeah,
the box is so the first step that we've taken is the embed microvisor example of how to separate processes from each other, which is at least tries to mitigate the risk of faulty software or malicious actors on your device, because they could break into one of your publicly network-enabled stacks that you happen to have on your device anyway, because otherwise you won't have an IoT device. Jeff? Matt's coming.
So I guess one, I think your question is that there's an inherent problem in it, which is that you're talking about providing services in order to provide certain measures of security, and you're talking about services that could be provided by the secure environment. So we end up in a recursion, right? Because that presumes the secure environment is secure, and that may indeed be the weak link in the chain. Particularly thinking of trust zone, we're talking about an eminently logical security system, not a physical one. So through row hammer or similar type attacks, if we can compromise this so-called secure environment, then all the house of cards that we've built on top is for nothing. So I don't mean to subvert the question or the conversation, but maybe we should be talking about whether or not that secure environment is actually secure, and if that isn't in fact the chief challenge.
Yeah, so those are services as well in my book with that regard. So protection against things like row hammer, big banging. I'm not a hardware expert, but as far as I know, the ARM way of doing memory isn't vulnerable to row hammer, but there might be similar kind of attacks in the future, of course. And those require physical mitigations in the MCU, because that's not something you can solve in software in a simple way. You can, but it requires a lot of redundant data, and that's something you definitely don't have on a constrained device, so that, again, makes life harder. Any other services, applications, physical protections we need to not forget?
A non-compromisable way of self-detecting the state of the device and self-healing of the device, or if it is not capable of healing itself, it should just shut down, and we need to provide some secure mechanism so that it cannot be overridden.
So you mean some live way of detecting the current integrity of the running the running OS code and the running application code if it hasn't been maliciously modified?
Yeah, and if it is, then there should be some level of guarantee that the device is not going to be operable anymore, or if it is going to operate, it's going to first heal itself and then operate.
Yeah, I think the simplest fix, of course, is just reboot the device if it detects that. But then you're still vulnerable in your next reboot, so then it depends on how easy or how hard and how present your attacker is on the network to compromise the device. But yeah, that's a good way of moving forward. Anything else?
Again, this is another basic one, but secure communications between different pieces of your system. Both actually, I think of a system that could be multiple devices as well. So security across that is tough to do well, and providing that as a service is very critical.
That's definitely tough to do, especially if you see that we get more and more multi-core systems in the Cortex world that need to communicate together. That's something we have to do well. So one of the things I didn't hear necessarily, but I'm not sure if people are worried about that, is things like physically protecting the memory against physical access, in the sense that people looking into it with the electron microscopes and stuff, because they have physical access to every device. Is that something people are worried about, or is that something where we say, well, that comes with the job of any computer and any CPU, so that's fine? Because there's devices where we care about that, like smart cards, where we have measures in place that erase the device or make it not working the moment something like that happens. Is it something we care about in IoT devices, or?
Depends.
Is the cost too high? I mean, that's
Medical device, probably. Yeah.
I think it's something you do care about, and I'm not sure how expensive it is, because you can always have the keys. If you have any on-chip memory of any kind, you can always decrypt the keys from memory to the local thing, put them in register, use them, and send it back. Or if you have actually crypto hardware, it's going to have that ability oftentimes. So it may not be a big cost to not keeping keys, ever having keys go through the DRAM.
Yeah, secure memory on chip, but that's often an expensive exercise. But yeah, that's definitely a way of handling it. Dan Han.
Yeah, thanks for that, Paul. Yeah, my name tab was wrong. If anyone's wondering why it was referring to. Yeah, so I think in terms of the RAMs, I think it's similar to the mobile world. You know, on chip RAMs are probably secure enough, but off chip probably not. There's also the non-volatile storage. Whether that's, how secure is that? If that's probable, then do you need to root the device in ROM, or is some kind of embedded flash solution enough? I guess it varies depending on the use case. But.
So I'm triggered by what you say at the start. So I come, as I said, my background is in the security world, and especially in the breaking of security world. And you say, well, off-chip RAM is not so secure as on-chip RAM, but that's, of course, that's a path that always is declining, in the sense that the capabilities, the public capabilities are increasing more and more without needing high-end equipment and stuff like that. And the design of new chips takes years before they actually come into market, and most IoT devices now are already built to be in place for 10 years, or not for a year in time. So those are things that if we care about them, we should be mitigating them now and not say, well, the capabilities aren't there.
You're right. At some point, it's going to be feasible to, flip the lid off and for the average person to get into that. I guess then when you start having to look at, hardware encrypted RAM solutions and things like that. But that's pretty advanced stuff. Maybe baby steps first.
Yeah, baby steps. Sometimes.
Generally build with flashes on these MCUs that are on chip are viewed as reasonably secure from these type of attacks or these concerns.
I think that's the current thought, that they are reasonably secure, because in order to program those, you have to either defuse or you have to directly program them, which is very hard to do, of course. But again, those capabilities will change. Yeah, so I'm definitely wondering what we as a community will do there to make sure that we can mitigate that fact in the future.
Maybe I can ask you a question that sort of follows up from before. How feasible are physical attacks where you decap an SoC to try and look at the flash inside, to your knowledge?
Unfortunately, quite feasible if you have enough budget. So if you look at very high-level SoC designs, like the one that most governments build for themselves in order to do secure crypto in devices. The Netherlands did one. I was project leader for that project. you see that there's a whole range of threats that are taken into account as being feasible either then with huge budgets or in the near future within a 10-year time frame with way less budget. And we've already seen university attacks on those kind of systems where they just scrape off layer by layer of the SoC till they get to the level where they can just with an electron microscope read out the current state of the memory. And that's already doable. It's a very, very slow process. You run a high risk that you break the chip, but it is something that's already being done in research environments. So that's why it begs the question on how we're going to keep that up in the future. But related to that, I think was what we were already talking about. In the Cortex-A world, we always have a big offline flash of the data, including the firmware. And because it's outside, you cannot trust the contents, and there's always a form of a key embedded in the chip that does decryption of that flash because you can't trust it to make sure that you have integrity and encryption of the data there before you start booting it. But in the Cortex-M world, that firmware is almost always stored in a flash inside the casing, meaning that basically you can say in most cases that you can trust what's in there because you as a MCU had to be able to, you were the one that was writing it, so if you can make sure that nobody can write there, that firmware should be trusted, and you don't necessarily need to do an integrity check at the start when booting, and you don't need specific keys to load that firmware, especially because those keys probably will be stored in that same flash, so you can't trust them either, or you have to have them hardware fused. So if everything is stored on chip and in embedded flash, how different does that make the secure boot model? Is it true that we can just say we trust that, so we can always start from that image? Do we need to do integrity checks anyway, even though we think we can make sure that it can never be written without our consent? And if so, how can we protect it? Because what are the other sources we have for protecting the integrity of the flash if it's not the flash itself? Dan?
I'm going to jump in. I've got the stick still. Yeah, so I think maybe you could just make some assumptions about the boot sequence is implicitly safe, but not necessarily the firmware updates system. So you still need to authenticate your firmware if it's coming over the air or something. So,
well, you need to hook on that. You need to authenticate during the firmware update process that the firmware is an integral firmware. But at that point, you are the only one that can write it, and you can write it down, and then you're again sure that what's in the flash is your protected integrity.
If you're making the assumption that we trust the flash, yeah.
Yes.
But if we don't trust the flash, then we need a ROM or something.
So, but if we don't trust the flash, what can we do then? Because how can we then ever trust what's in the flash? Because what can we use?
Ashley referred to stuff earlier. Maybe do some runtime integrity checking and things like
but what
that.
What do you use to do the integrity check? Because that's often stored in the flash as well.
Well, I think you do need some root of trust in terms of some one-time programmable memory or something to store it.
Yeah, but the software that runs that integrity check is again in that flash.
Yeah.
So then you need a hardware part in the MCU that does the initial integrity check based on an extra flash that only contains the integrity key to check that the flash is correct and they can boot from it. Because otherwise you have a chicken and egg problem.
You're right. I've not thought this through. I'm thinking out loud.
So a TPM is an option within. So for ARM, you have some form. You have a number of external co-processors that you can add, like the crypto cell that ARM has, that could potentially do that, but it's not something that's now by default in a standard MCU. So that's something we need to think about then.
I'm talking about external TPM. The external TPM still help with all those secure boot problems with embedded flash, or not? I have to think.
could, but the costs of a TPM are significantly higher than what's currently on the board.
In all of the discussions that I have attended in this conference, they have been focusing on the device security. What are the models we are going to put on the server side? I'm sure there should be some changes. Or are we assuming that it is inherently secure on the server side?
So what do you mean with what is inherently secure in the
So,
server?
so right now the servers that we have in non-IIT servers, they cater to a limited number of devices compared to what IIT is going to look like. The way we believe IIT is going to be is like hundreds of devices per person, or maybe not that much, but in that scale. Are we seeing any changes happening on the way servers are handled with that respect? Or are we confident that the server-side setup, the way it is right now, is secure enough and it can cater to the IoT needs, security needs as well?
Yeah, that's definitely an interesting question. I'm not sure that I can answer that. We have to do a lot of different things on the server side as well. I mean, the cloud is changing the way we transfer data and how protection is done. It also introduces a lot of new security risks that weren't there when you had your own private server rooms, especially related to the fact that we are now creating a large number of hives that are very interesting targets for state actors and hacker groups and to take down or to infiltrate. I mean, if you're able to infiltrate the Amazon AWS core infrastructure, you suddenly have a huge trove of access to data that normally is a scale that would normally not be possible. So yeah, I think we need to do a lot of extra protection in the cloud as well. But that's a whole different discussion that I would like to take somewhere else than in the Cortex-M discussion here.
I'm curious, kind of to any of the hardware vendors in the room, to the question on there as far as products that they may have today that do secure boot in the microcontroller space, and do they also do encrypted boot, or is it just a validation today?
We just use Cortex-A's, so I don't have experience with the M's at all with our thing, but we do secure boot, and people look at a couple different approaches for it. One is in fact we haven't talked about fuses, and that's an approach that some of these chips have used to store the very, very highest root key, or not even store the key. What they a lot of times do is they'll store a hash of the root. Yeah.
Yeah, I was just thinking your comment about booting internally. Our Wi-Fi chip boots externally, so it has a secure external SPI flash that it cryptographically signs and boots from. So we do have at least one instance that works that way. So yeah, we don't have anything like TPM or things like that inside, but we do have a secure boot that way.
Is it encrypted or is it signed, or is it a combination?
Both.
And that key is then inside and the mechanism for decryption is hardware inside of your...
Yeah, it's part of the chip fabrication.
Yeah. That sounds like a logical step.
Actually, what's your view on this?
Sorry?
What's your view on this?
So my view is in the discussion that I had with Dan. It's inherently there's an issue there without any extra hardware because you can't trust the flash. If you don't trust the flash, then all hell breaks loose because there's no way to trust the flash. So the only way to protect against that, and mechanisms that are used in other systems to do that, is similar to what Mark just described, is to have hardware capabilities in front of that flash to make sure that it's both encrypted and integrity checked at moments, so that at least you can see if it's externally manipulated. But at that point, after you've done that, there's nothing more you can do than to just trust it and to make sure that your update process is as secure as needed, because the moment that something goes wrong in that update process, it, under the wire, gets encrypted and integrity checked and put into that flash.
So since just one out of the flash, and when you ship out the product, you disable the JTAG, you cannot reprogram. So the only way you program is through your secure boot. So in that way, you still need to worry about the flashing everything.
So it depends how much you can trust a secure boot. And your secure update process, which can probably rewrite your secure boot process. So in the end, it all hangs together as a large number of different items, which there is a solution which introduces a new security issue, which is you sign it at the cloud side and provide the integrity at the cloud side, and that is put into the flash, and you're sure. But that requires you to know each device's integrity and encryption keys, which means you have a central trove where all the data is available to hack all your devices. So that's not pretty either. So yeah, it's a hard problem to solve. That's why I was interested to hear the different opinions of people here. Moving on. There's a lot of features in the A-World security infrastructure that we saw yesterday at if you were at the PSA presentation, there was a whole load of boxes with all kinds of capabilities and features that are part of the Cortex-A security infrastructure. Which one of those do we expect to actually be able to map to Cortex-M, and do we need them, or are all the capabilities we have on Cortex-A, are those also capabilities we need on Cortex-M? Because there's capabilities with regards to DRM and stuff that we probably don't need, but there's parts like secure boot that we do need, but the process is wholly different. But there's a whole load of other items that might be interesting. I'm not sure if anybody has an opinion about that. And otherwise, we're moving to the next question I have. So, as said, we have developed a first prototype of a way of doing a secure microkernel on Cortex-M devices using the hardware capabilities, for instance, the MPU in a V7M architecture, and trust zone for V8M as the base capability to do some form of hardware separation, hardware enforcement, but also hardware acceleration of those boxes, meaning you can have some form of trust between the boxes, and they can be you can have mutual distrustful engagements. But it also means that you as a developer, because we don't have multiple layers and dynamic loading and stuff like that, you have as a developer active involvement to be able to secure your system for each app and secure library, to have to protect it. So there's code required in secure libraries and code required in applications calling secure code in order to be able to use that. So for instance, this is just one little blob out of a big presentation we did a while back on Embedded Microvisor, which is public open source. It's available on GitHub. So if you want to dive into that deeper, I suggest you have a look there. But at the bottom, it's rather small here, but you see two microvisor box configuration lines that you as a developer need to add in order to make sure that you're able to call a secure function or to have a secure main loop that's not part of the regular system. So that means that something that is very, well, abstracted away in, for instance, Linux, where you don't have to think about security, it's already by default provided, and maybe you have to do some ACLs on a kernel level, but that's what you need to do, and then everything runs. Here, in the code, you have to make changes and you have to add lines and defines to make sure that your code will work. So it requires an intimate knowledge of the security process of the system, which is not required on things like a Linux system. So that begs the question, if that is needed, is it acceptable to ask active involvement from the developers of secure libraries and applications to actually create a secure IoT device firmware? Or is that a burden that's too much, and do we need to think about other ways of making this happen automatically, how convoluted or maybe impossible and constrained device that might be?
My gut response is that it's too much to ask, and it's for a couple of reasons. One, to repeat, my gut response is that it's too much to ask for two reasons. The first one is it's easy to get wrong. And the second one is because of the product managers and the product development environments that people work in. So the constraints there, if they're told that, you know, that what their core piece is that they have to work on, have to add something else, more often than not, it gets dropped.
Sorry. Matt, can you go to Abhishek? I didn't say that, Sean.
That's why.
Yeah, I think it's the other way around for me. If you had an infrastructure which does not allow me to modify it completely for my system, as system designer, I'm not happy. So you're defining a microvisor framework to adding security into things. It's a methodology, but you have implemented it in one way. There could be others coming along based on some sort of industry standardization. System designers will always want some control over what they finally put in. And no one's going to come into forums and say, we think exactly X, Y, Z are threats to our device. They're going to analyze it in themselves. So definition of ACL in microvisor and similar things in going forward, I think that will be part of system design work for specific applications. So I wouldn't think that that's a burden, but you know, you could define it in a way which basically adds a lot of headache, or you can define it in a way which is a bit more logical, and that's where I think just the balance is. I think I would like that freedom rather than the burden.
Okay, cool. Of course, the reason why it's in code in these kind of systems is because we have static linking and everything just needs to be in place. We can't do things at runtime to add these kinds of protections, which normally you can do on Linux kind of systems. Anybody else? I'm not sure what the time is.
Yeah.
Oh, so it's even closer. We're getting there. With that, then probably I'd like to thank all of you for your knowledge and sharing of that, and making sure that I think everybody here has a better understanding of what the Cortex-M security world will partake to make a better place.
Paul,
thanks.
Plug your. You're going to be in the hacking room with embed boards this afternoon. Is that right?
Yes.
And Sam is going to be around for a little while. Till 5. So if you guys want to go play with embed and talk to these guys some more, they're going to be in the light hacking room.
Yep. Thanks.